welcome back. And I'm going back to the AI questions where I was testing it on its electronics knowledge. If you recall, it got the first question wrong. So I'm going to go over this again with the AI a second time. Somebody suggested do it more than once. It might get it the next time. So I'll maybe go over it again. I've got answers for this, all these questions. So the first one here is easy. I don't need to really go over that. But the current IT here is 12 amps. It should be here. I think it got 9 amps the last time. The reason I think I got it wrong is it thought these were in series. I think it confused the fact that these two in parallel are in series with these three in parallel, and it perhaps got confused there. I'm not sure. Once you've got IT, you can find I1 or I2 by the current divider rule, and you'll find that I1 is, this current is about 5 amps, and this one is, what's that? Hang on, just hard to see here. 7 amps, 5 amps. So this is 5 amps and 7 amps here, and that makes 12 amps going through IT. But the reason I'm giving it, I mean, that's not such a difficult question, but I'm giving it a slightly harder one. Some of you might think it's too hard, but the whole point in giving it these questions is that it's supposed to be heading towards AGI, Artificial General Intelligence, which means it's got to be better than a human, or at least most humans at most things. So it should be able to work this out, which is equivalent of a first-year electronics paper at some kind of university. It's a particularly easy question as regards Kirchoffs laws goes. It's one of the sort of first ones you might go over, with students. And if I can just go over it myself, so I can ask it, let's say, to work out I2, I1, I3, or the voltages across these resistors. Notice that voltage, 10 volts, is in opposite polarity to this one. It's 6 volts. And if you've forgotten how to work these things out, you need to sum the voltages, of course, around this loop and around this loop. So there's going to be simultaneous equations usually associated with this. There's other ways you can do it. You can use nodal analysis, but that really is the same thing. You can call that node there VA, let's say, and sum the currents into there. Then you get 10 minus VA divided by that equals this current from that current, which is sort of Kirchhoff's current law, really, nodal analysis, but written in terms of the voltages. Anyway, so I'm going to do it the normal way, and I'm also going to show you a way that if anybody is like in first year and they struggle with these kind of questions, a way that you can do it so you never really get it wrong. And then I'm going to ask the AI how it does it, and see if it can get the right answer, because I didn't really get back to this question. I sort of let it slip, moved on to the op amps, because the op amps were my main thing, but I thought I'd come back to this one. So the thing to remember is that with the convention that we use is doesn't matter which way the current's going, but the voltage must go in the opposite direction. And of course, in real life, you can think of it the other way around if you want to, but you've got to adopt a convention. Whatever convention that you actually have, you must stick to it. And this is usually the conventional current one, where the current flows out of the positive. That's why in the same circuit up here, we've drawn the current I1 as coming from the positive, even though it might be coming from the negative. I mean, no, in reality, the current actually flows along the outside of the wires in a field. So, I mean, these are just lumped parameter approximations anyway, so we don't need to get too worked up about it and say, oh, that's not what really happens, because what really happens is a lot more complicated anyway. Anyway, so you've got a current going through whatever the conventional current that way. We assume that the arrow is going in the opposite direction. That's important. And we always label it such. And for a voltage source, we always label the bottom of the arrow negative to the tip of the arrow positive. So this one's upside down because it's like -6 I don't call it -6, so I just put the arrow in the opposite direction. And then what we do is, if the arrows are head to tail, we just add them. And if they're head to head or tail to tail, we subtract them. So this arrow and this arrow are head to head. So whatever voltage this is, I must subtract that one. That one must be negative relative to this one. And the same with this one, because it's head to tail. Sorry, that's this one's going to be 10 minus I1 R1 or 2I1. And it's going to be minus again because it's head to head of that one. So these two add up together because they're head to tail, and that one's the opposite polarity. So it's 10 down here minus 2I1 by Ohm's law, 2I1 minus 8I2, and we don't know what I1 and I2 is, and equals 0. So we're summing them up to 0, the algebraic sum of the voltages. So you see what's happening. It's the arrows here that's important. Now this one's perhaps more difficult to see because you normally think sort of simple circuits if you're at school or something, that the voltage is on the left hand side, so it's on the right hand side and it's going the other polarity, so that confuses people. But here we've got, we'll take that to be positive just like this one, so that's going to be I2 R2 or 8I2. And then this one, because it's head to head again, it's going to, of the arrows, it's going to be minus I3 R3 or minus 4I3. So 8I2 minus 4I3. And this time it's going to be plus 6 because it's the same direction as this one, even though it doesn't kind of look, if you sort of pulled the loop out, you'd see that this guy and this guy are the same polarity. That one's going in the same direction. It doesn't look like it there because it's going down, but if you pulled the arrow, followed the arrow back, it would be hitting the head of that one's hitting the tail of that one. So you've got I2R2 minus 6 or plus 6 minus 4I3 equals 0. So you get two equations. And once you got them, the rest's easy. I mean, you don't need to, the rest's just algebra. And you can solve them any way you like, but of course you can't solve it at the moment because you've got 3 unknown, you've got a third current. But we know by Kirchhoff's current laws that the algebraic sum of the currents is 0. So we can say that I1 is equal to, well, what's going in is equal to what is going out, which is the other way to look at it, like water going in. So I1 is equal to I2 plus I3, obviously, because that's I1's going in and this is coming out. If you look at it quickly, you might think, oh, I3 is equal to I1 plus I2, but it's not, because that was going in and those are going out. So I1 is equal to I2 plus I3. So we can rearrange that and get I3 is I1 minus I2. And then we can substitute this back into this guy here, because we've got I1 and I2 in equation 1. We've got I2 and I3 in equation 2. So just substitute the I3 into there, and we get another equation. So we've got the original equation 10I2 minus 8I2 equals to 0. We get another one once we substitute this one into here. And I've written them in matrix notation. Usually in first year courses they spend a lot of time doing Cramer's rule. Is it Cramer's rule or Cramer's rule? Which is a sort of trick to solving equations like this. But I'm just going to do it the old-fashioned way and invert a matrix, which mathematicians hate you doing that, but since I've got MATLAB in front of me, there's no point in fiddling around with working out the determinants of matrices. I can just stick it into my package and use the tool. So there's nothing wrong with using the tools. I mean, if I was doing this now with students, I'd allow them to use any tools they like, because the important thing really is to get to these equations. That's the main part of the question, and to do that substitution to get another equation. Although to solve them is just a really a kind of trivial matter, really. It's just nowadays, because we've got so much software. Anyway, so we end up with I1 is 3 amps, I2 is half an amp or 500 milliamps, and I3 is 2.5 amps. Then we can, if we're just asking for those currents, we've got the answer. But we can also work out the voltages across these resistors. So I1 we know is 3 amps, so it's going to be 6 volts across there. But notice, so 6 volts across there, there's 10 volts here, and notice again it's head to tail, it's 10 minus 6, so the voltage at that node is 4 volts. It's not 10 plus 6, which again is another mistake people would make, students would make. It's 10 minus 6 because the arrow is going by our convention. The heads are hitting one another, so that one's subtracted. Of course, you can put plus and minus and so on in there as another way. If you don't want to put arrows in, that's another way you can do it. I find the arrow method is by far the simplest way. I don't know who first thought of the arrow method, but I've done this for so long now. I don't know if somebody at some point said do it this way and you never go wrong, and that's very true. You can use the other one with so-called Maxwell circulating currents, and I never knew Maxwell actually. I assume it's James Clerk Maxwell ever did circuit analysis, but maybe he did. Who knows? But I don't know where that when the people talk about Maxwell's circulating currents, where the paper is the original manuscript where he said you can do it that way, and I don't think it's a good way of doing it. That's when you start making mistakes, when you just have a current, let's say I1 in here and I1 around there, and then you have I1 minus I2 in here. I think that's an easier way to make a mistake than doing it the old-fashioned way with arrows and currents. It may seem a bit clumpy the way I'm doing it and old-fashioned, but at least you end up with the right answer at the end. That's the current. So I'm going to ask the AI to remember these currents. I1 is 3 amps, I2 is half an amp, I3 is 2.5 amps. Let's see what the AI comes up with and if it can duplicate any of these equations. Hello? Hello?
Hello there. How's it going? Hi, how are you today?
Hello, can you speak with an Aberdeen accent from now on, please?
Aye, I can do that. How can I help you today?
Okay, so I've got some problems for you in electronics. Now, can you see this circuit diagram here?
Aye, I can see it. What would you like help with on this circuit?
So, can you tell me what the current IT is through the point C, at the node C, what the current IT is in this circuit, please?
Sure. To find the total current IT at node C, we need to determine the equivalent resistance and then use Ohm's law. First, we find the equivalent resistance of the parallel and series combinations. Then, we can divide the total voltage by this resistance. Let's work through it step by step.
Okay, so what are the 3 resistors in parallel, what do they come up to be?
For the resistors in parallel, 1, R3 is 60 ohms, 2, R4 is 20 ohms, 3 is 30 ohms. The equivalent resistance, R345, is calculated using 1 over R345 equals 1 over R4 plus 1 over R5. Substituting the values, 1 over 60 plus 1 over 20 plus 1 over 30. Calculating this gives R345 is 10 ohms.
Okay, good. Now what about the other 2 resistors in parallel, the 2.4 ohms and the 1.7 ohms?
For the resistors R1 24 ohms and R2 1.7 ohms in parallel, the equivalent resistance R12 is 1 over R1 plus 1 over R2, 1 over 24 plus 1 over 1.7. Calculating this, approximately 1.61 ohms.
Are you sure about that?
Let's double check that. The formula for parallel resistance is 1 over 1 plus 1 over 1.7. For R1 is 24 ohms and R2 is 1.7 ohms.
Wait, that's 2.4 ohms, not 24 ohms. It looks like it's 2.4 ohms and 1.7 ohms.
Got it. My apologies. For R1, 2.4 ohms, and R2, 1.7 ohms, the 1 over 2.4 plus 1 over 1.7 is about 1.9 ohms. So the equivalent resistance, R12, is about 1.0.
Ah, good. So tell me then what the current IT is through the circuit.
To find the total current IT, 1, we combine the two equivalent resistances, R12 and 345. Our total is R12 plus R345, approximately 1.0 ohms. 2, using Ohm's law with a voltage of 132 volts, is 132 volts over 11 ohms equals 12 amps. So
Okay.
the total current I...
Good. Excellent. Now, can you tell me... oops. I have to start again. That was spot on, by the way. Eventually. Let's go again. Hello? Hello?
Hello again. How can I help you now?
Yeah, the same circuit as before. Can you tell me what I1 and I2 is? Just tell me the answer rather than the details. I1 and I2. And remember, R1 and R2 are 2.4 ohms and 1.7 ohms.
Sure. For the currents I1 and I2, I1 is approximately 55 amps. I2 is approximately 77 amps.
Now
These are the individual...
wait a minute. So
Yeah.
what did you say IT was?
The total current IT was calculated as 12 amps.
Oh.
If you have any other questions, feel free to ask.
So how can I1 and I2 be bigger than 55 amps? Sorry, 12 amps.
You're correct. Yes, my mistake earlier. Given IT is 12 amps, the currents I1 and I2 should be much smaller. Let me recalculate. For I1 is the voltage over R1, 132 volts. Then, for I2 is the voltage over R2. For I2 is approximately 177 amps. But both of these currents doesn't match IT. It seems I made a mistake in the initial explanation. Would you like a step-by-step recalculation?
No, just remember that R1 is 2.4 ohms and R2 is 1.7 ohms.
Got it. With R1 equals 2.4 ohms and R2 equals 1.7 ohms, the total current IT needs to be partially divided based on the parallel resistors. To find I1 and I2, I1 is 32 volts over 2.4 ohms, and I2 equals 40 amps between these resistors. But since IT is the combined current, we should actually calculate the voltage across the parallel combination first, and then distribute the current accordingly. Let's recheck if you'd like the precise values.
Wouldn't it be easier just to use the current divider rule? You know, the current divider rule? Current division.
Absolutely. Using the current divider rule, for I1, IT times R2 over R1 plus R2, and I2 times R2 to be 55%. Substituting the values, for I1, IT times 55 over 1.7, approximately 5.44 amps. This way, I1 and I2 add up to IT.
Great, thank you. Right, another problem. Here it is here.
Sure.
So this is a circuit with two DC sources. One is plus 10 volts, and notice the second one, 6 volts, is in the opposite polarity. And I'd like you to calculate some quantities for me. Can you do that?
Absolutely. Just let me know what quantities you'd like to calculate, and we can work through them.
So can you tell me what I1, I2, and I3 are? Without doing the, just actually tell me the answer.
Certainly. Here are the answers. I1 is 3 amps. I2 is 0.5 amps, and I3 is 1.5 amps.
You sure about I3? I3 must be equal to I1 minus I2.
You're right. I3 should be I1 minus I2. Given I1 is 3 amps and I2 is 0.5 amps, I3 is 3 amps minus 0.5 amps. So I3 is 2.5 amps. Thanks for pointing that out.
That's good. Can you tell us the voltages across R1, R2 and R3 then, please?
Certainly. Here are the voltages. Voltage across R1, VR1, is I1 times R1 equals 3 times 2 ohms, VR1. The voltage across R2, VR2, is I2 times R2, which is 0.5 amps times 8 ohms equals 4 volts. So the voltage across R1, I2 times R1 is I1 times R1, I2 times R2, this equals 6. Or I2 times R1 equals I1 times R2 plus R2 times R1 equals 0.5.
Good, thank you very much. I think that's it's correct, so that's well done. Thank you.
You're welcome. Glad I could help.
No
If
bother.
you have any more questions.
No bother, okay.
All right, take care.
And if we look, well, I have to do it the difficult way because I'm not, unless I go back to if I go to ChatGPT, I should see the transcript. And you can see I don't know how well you can see it here because I haven't got the screen capture as such, but it's got all the equations here. So it got us in the end. So for the first question that I could maybe see that its eyesight wasn't that good because it didn't see the decimal point and let it away with that. And it once it knew that, but it still didn't get the currents right in the two resistors because until I told it about the current divider rule. The second one, which I thought was more difficult, was the Kirchhoffs laws. It did really well on that and got it spot on. So there it is. Thank you.